Welcome back. Previously, what we have covered is simple linear regression with the Boston housing dataset. We perform robust regression as well as evaluate the model performance. In this video, we are going to go through an expansion of the linear regression model. We're going to move into multiple regression. Now, simple linear regression is linear regression with univariate, meaning single feature to explain our target variable. Now that we move into multiple regression, in essence what we are looking at is multiple features to predict the target variable. Now let's start with this multiple regressions. This is what is really familiar to those who have been through either high school or university or graduate level statistics. This is the basic formula of y being your target variable, beta 0 is your intercept, beta 1 is your coefficient, and x being your target variable. So this is a simple linear regression with univariate. Now as you start working with multiple regression, then you start looking at with x1, x2, and on it goes. That will be what it looks like. So the first line here is simple linear regression. The second line here will be multiple linear regression. In the examples that we did with the Boston housing price prediction, we were doing or modeling mostly with simple linear regression. Now the one time that we did multiple linear regression was towards the end, whereby we use everything in our model to actually conduct our so-called modeling process. So that's really at this part whereby we use everything. So this part here, basically we actually use everything to conduct our linear regression. So that's where the performance evaluation we actually did perform the multiple regression, but I didn't really go into a deep explanation of it. So this is what this video is really for. Now, multiple linear regression is a well-studied field in statistics. Now, our focus will be on what is relevant for data science, which the predominant focus is in practical, and really what's relevant for prediction. Statistics has a slightly different focus, which is in the so-called the coefficient, the robustness of it, and the biasness, and the rest of it. So let's start with this. A couple of things we wanted to import is your NumPy, your pandas, matplotlib for visualization. I've added a new line here that I haven't explained so far. It's rather than plt.show, I'm going to add this, so every time when we actually do plot something, it will just get plotted within the Jupyter Notebook itself. Now the other thing is that the last time what we did do is that we downloaded or provided the data sets in the folder and the zip file for you, so that you can actually start playing around with the Boston housing. Now within scikit-learn, the same data sets is also available. So I just want to show you a different way to actually load the data. So from scikit-learn data sets, we import load Boston and we store the load Boston into Boston data, and we convert the Boston data and adding the column name, which is the features name, into the data frame, basically convert it to a data frame before storing it into the variable called df. So if I print that out, this should look quite familiar to you, with one exception. What is the exception? The exception is that you don't see the median house price value here. So in essence, this is a features matrix that we talked about last time. Let's look at the number of data. We have 506 rows of data and 13. Basically, the 13 is across the columns, and we're storing the so-called all of these into x. X will be our feature matrix, and the target variable we store it in y. So let's just print y out so that you can actually see what it looks like. This is basically our median house price value. Okay, so we've got the data loading and basically preparation ready to go. Now, rather than using scikit-learn in this lesson, I'm going to use the stats models that is provided for in the Python library. Let me pull that up across to show you. Here it is. The stats model is really for statistical modeling, and there are actually a lot of stats tests that you can actually perform within this, and as well as statistical data exploration. So we're going to make use of this. I just want to point you to this so that you know where to look for it if should you want to actually conduct more so-called statistical analysis. So let me move this away. Right, so there are two parts here that we are importing. First is the statsmodels.api. We're storing that as SM, or importing as SM. The next one is the statsmodel.formula.api as SMF. We'll go through that, make use of that a bit later. Let me just remove that. Okay, so there's a slight difference in the way that stats model, how it's actually created. Is the construction is a little bit different from scikit-learn. You do need to add an extra constant term simply to allow the bias to be estimated on itself, meaning standalone. Otherwise, the bias terms or the intercepts will be incorporated into your coefficient estimation, so your coefficient will be incorporated. So we want to actually segregate that out so that we actually have a clear constant term on its own here, as you can see here. Again, I won't run this cell. If you want to actually have a look at how stats model call the ordinary least square library, just run this cell. It will show you how or what are the actual input parameters you need to provide. Here we are running the SM .ols, which is the ordinary least square, and providing the target variable as well as the x constant that we created here, and we instantiate and also fit our model. So the fitting part is done here. We're storing it to the LR, and we'll run the LR stands for linear regression. So once you run this, notice that there are a lot of information that is generated. This is pretty typical of stats, where you have the ordinary least square regression results here, and then you have the coefficient estimates, which is along this line, and the standard error, and then the t-test, as well as the p-value, and some more residual stats that's being provided here. So let me walk through these one by one, because these are really important, especially in the field of statistics and multiple regression. A couple of things. There are a lot of stats tests and information here. These are mostly for stats analysis. You don't really need all of these for data science, but it's good to know. Let me just correct that typo there. Again, I mentioned before, data science focus is really on prediction and having a model that works on predicting real data or unseen data. It is not concerned as much with the correct specification of statistical problems. Okay, these are all the descriptors to explain to you what each and every one of these fields are. The dependent variable really is the target variable. In our case, is the median house price value, so it's provided here as y. The model that we're using here is ordinary least squares. The method of achieving the estimates coefficient estimation is using least square method, which is the standard method. So the number of observations is provided for, is printed out. The degree of freedom in terms of the residuals, this is calculated by taking the number of observations less the number of parameters that you use to estimate. And the degree of freedom of the model really is the number of estimated parameters in the model. So here we have the model itself is 13. The degree of freedom of the residuals is the number of observations less the number of parameters you use to estimate the model itself. Couple other things. R squared, this is the coefficient of determinations, and it measures the goodness of fit. I won't go through these in detail. In essence, it's basically telling you how much your model is, and I can explain the variability of the underlying data itself. The adjusted R square is something that you will use. I haven't mentioned that earlier in our previous lessons, because typically adjusted R squares is only used in multiple regression, not in linear regression. Now the adjusted R square is used and make adjustment for based on the sample size and the number of parameters used. So when you have the more parameters that you add into a model, typically the R-square will go up, because in some way, shape or form, the so-called variability is explained by the additional parameters that you put in. But is that significant? So what adjusted R-square is trying to do is it penalized the so-called additional parameter you put in that doesn't actually add much to the explanation of the underlying variability. So that's really where R-square, adjusted R-square comes in, and typically it is used when you're comparing multiple regression model. The F-stats tells you that whether your model is different from just simple average or not, and typically you read the p-value of F-stats to see if it's below 0.05 or not. In the past, 0.05 is used commonly because the olden days when the computational power is not very powerful. Nowadays, people start to advocate basically a value that's substantially smaller than that, such as 0.005. The last two is the Archaic information criterion. I'm sorry, I'm not used to reading this. I just use called AIC. This evaluate the model based on the model complexity and the number of observations. The lower the number, the better it is. And BIC is very similar to AIC, except it punishes models with more parameters. Again, the smaller the number, the better it is. And by itself, it doesn't actually mean much. So these are the two numbers here. That pretty much explains the first table. And you can see here the p-stats here is very, very small, 10 to the power minus 135. In essence, what that's telling you is that the model that you have is significantly different from an average model. Okay, so other tests that's provided, the following table, which is this portion here, basically is a long list of the coefficient as well as the standard error. Typically, when you're reading this table, what you will look for is this p-value, because the coefficient by itself doesn't mean much. With the standard error, unless you want to manually calculate it yourself, it also doesn't mean much. T-table, you need to usually compare it against the T-table, or the T-stats. You have to compare it to a T-table. Again, that's very tedious. Hence, people mostly use the p-value as the way to read the significance of a number. And what you can see here is that the indus is insignificant, age is insignificant, the rest is significant. All right, so that's something to actually pay attention to. So indus as well as age is not significant in accordance to the number associated t-test that's provided. The last column, two columns, basically is the 95 confidence interval. What is shown here is the 2.5 and also 97.5 percentile. Okay, the last table provides the information in as far as the residual test. In statistical modeling, the residual is what's being paid attention to substantially. The reason being, from the residual after your model has explained the variability of the data, what is left in terms of your residual should be random, okay, with normal distribution. And if it possesses or exhibits some sort of behavioral pattern, or not so much behavioral pattern, certain patterns, it means that there are some, your model has missed out on some signals. Okay, so a couple of things that you pay attention to is the omnibus. This is basically a combined statistical test for skewness and kurtosis. What is skewness and kurtosis? Skewness tells you whether your distribution of your residual is to the left or to the right. So a positive value means there's a long tail to the right, a negative value basically a long tail to the left. Kurtosis measure the pickiness of your distribution. If you have a negative one, meaning it's actually flatter than normal distribution. If you have a positive one, meaning it has a high peak and also extreme tail. So those are the two things that you pay attention to, and both indicates some problem with your models. And typically, people either read the omnibus or the Jagbarak, but usually you just read the p-value of these two. Again, p-value of less than 0.05 indicate significance. Now here you have the p-value here is very small, meaning it's significant. So there are some more patterns that's not being modeled with the features that we provided here. The same Jagbara also indicating the same problem with the model that we have. The last two figures I want to actually cover is Durbin-Watson. This is only useful for time series modeling. This is a test of the presence of correlation amongst the residuals, especially from a time series modeling point of view. And the conditional number is a test for multicollinearity. Anything that's greater than 30 indicates unstable results, meaning within your data, some of your so-called explanatory factor share the same variance, or the other way to put it is that one has an impact on the other, or they are correlated. Okay, the last thing that I want to cover in this video is really stats models formula.api. Now what we did do earlier is in terms of the way that we model it is very similar to scikit-learn. We provide the target variable, we provide the x without specifying the so-called formula itself. You can do it this way. This is the way that most people are familiar with. If you come from a SAS background or R background, you just provide the formula. The so-called target variable is basically explained by these factors. So you can run that and print the summary. It will provide the same result as previously. That's pretty much the end of this video. What we've covered in this video really is an introduction to multiple regression and how to conduct your modeling using the stats model. And the third one that you did is the actual so-called understanding of the so-called stats output itself. What I'd like you to do as an exercise is pause this video for a couple of minutes and try to actually select a portion of this. Let's just say from constant all the way to RM, and run your model using stats models and see what the generated number looks like. So again, until RM, run it and see what it looks like. So just pause the video now and try it out. When you come back, you can compare against what I've done, and or rather the result of the exercise that I'm asking you to do right now. Let's pause this video. All right, welcome back. How did that go? I hope you try that and see what it looks like. And basically, it's a really interesting exercise for you to actually try it out to see if you can actually model using these 4 variables. Now I cheated. Rather than using the data frame here, what I did do is actually I used a shortcut and just used the formula as such. And when I ran it, this is my output. So I'm going to leave this notebook for you to compare your results against mine. And just for you to actually play around with the exercise and see whether your results looks exactly the same as mine or not. So well done for trying that out. So in essence, this video we've covered on multiple regression, and we also used the stats model and to actually perform our stats and also modeling, and to actually generate the actual coefficient itself. And the last thing that we did is actually use the formula API of stats model to actually generate the same value. So in the next video, we are going to go into looking at the different features and identifying collinearity between features, and also trying to select features that or dropping features that is irrelevant to our model, and selecting features that is of high importance to our model. I look forward to seeing you in the next video. Thank you.